We occasionally are graced with speakers from this related part of the technology world. You can see more about them and their charter here, and I will hand things over to Professor Lin.
All right, so good morning, good afternoon, or good evening, depending on where you are. So my name is Zhiqiang. I'm a professor at the Ohio State University, and I'm part of the CDCC Center. So I have been working on TE for maybe the past 10 years. So today, I think it's our great pleasure to present our most recent work on the sticky policy. Since my student Zhiqiang, right, he really did the work, so I will give the floor to him to introduce our work. So Zhiqiang. You can unmute yourself.
Hi, everyone. So my name is Zhiqiang Zhao. I'm a PhD candidate working at the SEC lab at the Ohio State University with Professor Lin. So this is our work at the CDCC, which is about collaborated and private data processing using sticky policy. We gave it a name called STATES. This is a joint work with Purdue with Professor Ninghui Li. So yeah, it's a very fun work, and let's dive into it. So first of all, acknowledgement. So we like to thank NSF this work. And so basically what we want to achieve is something, so this thing has a lot of names called sticky policy or policy attached data or policy carrying data, a lot of names. But basically what this technique has been there for a while. It tries to tackle a problem in conventional like access control, which basically in conventional access control, you try to embed everything in the code. It's like, for example, administrator can or root account can access, but regular user can't. So this is kind of like a simple policy. But for sticky policies, like you want to attach the policies to the data so that you can have different policies for different kind of data. And it's more than just like authentication and stuff. You can put basically like whatever you want into the data, as long as your policy can specify that and you have a way to enforce it. But there are many problems about existing solutions that they doesn't seem to support anything beyond access control. So for example, there's no data in use protection, and that means once the data's like be decrypted and being allowed to access, you no longer have a way to control how the program uses the data. And also about data lifecycle protection is that when you so the data will eventually grow an output out of it. Otherwise, why you want to process the data? So eventually you got to have some output. But the output is like, what policy should you attach? So these are called derived data, the data derivation. So what policy should you attach, and what kind of data can be allowed to output? So these are all just like unsolved in the existing sticky policies solutions. And also about dynamic collaboration. So it's like when we got multiple parties, it's not just you, not just your program. It's about a lot of people, different people who are like mutually distrusted. So how are you going to solve this? So for these three questions, like people try to give their solutions. Like for data in use protection, there are like different kinds of encryption-based access control. But they all have to eventually trust the application, and still, so after the decryption part, after the access control part, you no longer have like you can no longer limit how the program access the data. Like for data lifecycle protection, like we said, how are you going to protect the output, right? What's allowed in the output? So what policy should be attached to the output? So let's take a motivating example. So we talk a lot about concepts, but let's see a concrete example. One of the most common thing the hospitals are trying to do right now is that they try to use utilize artificial intelligence like machine learning to train a model that can classify like diagnose some diseases, for example, cancer. So what they're going to do is that they're going to have a lot of like medical records that are so private and confidential and privacy related, and also regulations forbids you to like output the data to show the data to anyone. But they have to use the data to train a model. And so what's going to happen is that so you want to protect all these like medical records, but besides of that, because it's a jointly trained process. So the first question you want to ask is how to make sure like how to limit my data set, right? For example, some hospital might not want their data set to be like over 30% in the entire like training set. So how do you achieve that? So that's a policy. You can see that's a policy. And then like we said, how do you guarantee the confidentiality of the training set, right? So once the data set's used to train, now you got the model. But the model is actually jointly owned. So everyone who contributed to the model should be an owner, but it's like, how do you limit the fair use? For example, if I just contribute a little bit towards the model, but I use it a lot, then that's not fair. So you can see this is actually a policy on the model. So this is what we want to enforce on the derived data. So model is a derived data. And also, how do you safeguard the model? Like the model, you can't just leave it there, right? So if you leave it there, then everyone can access, not just those who contributed the training set. So once you got the model, another thing a lot of people might do, like for example, the hospital might want to use some even more private data to fine-tune their model. They don't want to contribute it to other hospital. They just want to have a fine-tuned model. So first of all, is that even allowed? So you can see this is a policy. So do you allow like a hospital who can use the model to fine-tune it? And also after fine-tuning, the model should be exclusively owned by the specific hospital who fine-tuned it. But it has jointly owned bits. So like the previously said fair use policy, how do you want to enforce that? So there are a lot of like these questions on it. You can see you want to have something on the input side. So you want the input policies should be guaranteed on each data. Each data has their own like policy. You want to have policy enforced on the output side. But besides of that, the entire processing must also be safeguarded. So when we look at these three questions, basically what we try to do is that we want to solve these questions using TEEs, using the trusted execution environments. So our proposed solution is that we want to have a TEE enforce trust and isolation so that everything can be attested. You know what's going to happen. But besides of that, like the common like what we commonly know, the cryptographically encrypted transmission, we also want to have a sandbox access. That means the program running inside the TEE somehow guarded from like doing anything it wants. Because currently you have to trust what the software inside the TEE. You have to trust everything inside the TEE. But we think that's overkill. You shouldn't count on that because some software may have bugs. So we also want policy enforcement for both input and output so that we can achieve what we said. We need to have a commonly like packaged like it's something like a protocol, but like a data structure for the policy attached data used here. So our design is that we have a payload that is totally encrypted. So it has your data, it has a policy, it has like your data attributes, and it is totally encrypted. But we also need something to help the program to get the key. So you need to know some information so that you can use it for remote attestation to get the key from a remote like server or like the original owner. So it's going to be something like this. So with this, model the workflow of the data. So the workflow what we found is that basically follows a producer consumer model. So the producer generates the data, and the consumer is going to use the data. But it's very likely that the consumer is also a producer because after it uses the data, it's going to generate new data. But what we also want to detach is that we want to detach the owner, which we call the custodian, because it's like a legal term. It's a technical owner, so we call it custodian, so that it owns the data. It also owns the producer infrastructure. But what we want to do is that we want to grow this model into a full like workflow. So this is our workflow skeleton. So you can see the producer is going to produce the data and the consumer is going to use it to generate new output. But you may find that here we also have something called a key delegator, which we'll introduce later. So the entire workflow, it looks like this. It looks like a very large and complicated workflow, but we're gonna talk each step of it. So for the first step is that the data producer is going to be deployed, and the data custodian, which is if you still remember, is the technical owner for the data, is going to provision the key and the policy to the data producer. So it's going to also provision the key to the key delegator, which we're going to talk about later why it's there. So the data producer is going to generate data because it's a producer. So it's gonna have all those data attributes ready. So the attributes is tied to the policy. It's like what the policy wants to know about the data. For example, like we said, like the medical record, we talk about how many medical records are there in the raw data. It's going to be an attribute. So the data custodian and key delegators information is going to be made into a metadata so that the consumer can later use the metadata to find the key. Then it's going to be encrypted and packed into the policy attached data we talked before. So this is basically about the producing, like generating the data. The fun part is about using the data because that's where things could get leaked. So let's now see how it's going to be used. How's data going to be used? So in the data consumer, what's going to happen? So we want to use a sandbox to have the consumer program, the actual consumer program inside the sandbox. And so they're going to have a data. So we have a data set infrastructure. That means the that before and have the policy checked over the entire data set before it's allowed to access. So that's how we can enforce like the percentage, like you can't be over 30% of the entire data set. So this infrastructure is there to support that. And here, you can't expect the data custodian is always online. So what's going to happen is that you'll want to have a server there. It's like a service. It's like a TE protected service in the cloud that's running like 24/7, so that you can always go there to fetch the key. And because it only holds the key, so it's a very simple, like enclave protected one, and you can use it remote attestation to do that. And the key is only provisioned to the data consumer when the attestation is passed. But note that it attests the entire like data consumer enclave. But the problem is that the consumer program, like we said, we want it to be sandbox, and that essentially means it's not trusted. So it's not part of the attestation, and we'll talk about how we do that, how we're going to do that. So you only attest all the rest of the infrastructure here in the data consumer side. So after the attestation, then you provision the key to the consumer side. You can decrypt the data, and if the policy check is passed, you can you go and consult the policy engine. The policy is passed, you can go into the you can provision the data to the consumer program to allow it to access. But the consumer program is eventually going to generate some data. So you have output data, you have like all those attributes and proposed policies. The problem is that we can't allow it to just go directly output these stuff, because first of all, it's not like encrypted into a policy attached data or the pad. And another thing is that you can't say if these output or policy complies with the original data's policy. So what we're going to do is we're going to have it go through the policy engine. So the policy engine is going to check it against the existing policy, and if it passed, you can have a check policy, check the output data, and these stuff. It's going to generate a new key, and it's going to encrypt it, and the new key is going to be like just like the data producer. New key can be provisioned somewhere to a certain key delegator. So that gives us an output pad, the output policy attached data with all the output and policy checked. So you can see that the most important part here is actually in the consumer side, because if it's not trusted, it is where it could get leaked. So in our model, we have sandbox, we have like policy engine, we have all this IO protection, and we have like we need to build up the trust using remote attestation. So how does that translate into an architecture? This is just a model. So what we're going to do is we want to have a middleware. Actually, the middleware is going to be used to achieve those. And we use runtime, a programming language runtime, for example, like a Python runtime or a WebAssembly runtime. So we use a WebAssembly runtime to do that. So by using a runtime, we actually have more benefits than just having a sandbox. So of course, we can achieve all those IO protection. But also because there's a runtime already, we can support a very complex like policy engine and a very diverse policy engine. You can have all different kinds of policy engines implemented in the language that the runtime supports, or in the language that can be compiled into the runtime languages. So by having that, we define a set of APIs so that the policy engine can achieve all those input and output check in those pipelines. And we also develop an architecture independent framework. So the framework is actually written in C and C++, so you can just basically compile it and run it anywhere. So we detach the TE support and the runtime, that you can have different kinds of runtime, you can have different kinds of TEs on the bottom. So we implemented this architecture, and so our demo prototype is based on SGX and WebAssembly. But like we said, these two can be swapped to other TEs and runtimes, as long as you put you put an API translation here. So we have APIs for those. You just set. So we tested the performance for the whole system. So the first performance in our evaluation test is that the data access overhead. So that's a very important thing here, because the policy check and the key fetching, particularly the key fetching, is relatively heavy. So with or without key fetching, the performance to go through the Ethernet, you need to go through the entire remote attestation procedure. You can see that most of the overheads were taken by the key fetching process and remote attestation process, but still it's about like 100 milliseconds. So similar to what you would expect when an attestation happens. But if the key's already been fetched to local, so for example, if you are reading two data sets from the same party using the same key, then you can see that the access is actually very fast, even when the policy evaluation is involved. So overall, it's basically about the key fetching is the main overhead here. So to test a relatively compelling use case, a more like close to real world example, So like we said, we want to. So our motivating example is about like hospitals training a cancer detection model. So we also train a cancer detection model using the Wisconsin data set, the Wisconsin breast cancer data set using the SVM to build the model. So we consider like 3 hospitals. ABC is going to train the model, and the model is trained on hospital A's machine, so it doesn't have to fetch hospital A's like the keys. And each of those have three data sets to contribute. So in a total of 9 data sets. And from the timeline, you can see that the first time when you try to load the data set, it has to fetch the key. So from the timeline, you can see that it costs about like 150 like milliseconds for the first one, 100 milliseconds for the second one. But after fetching on those, basically all the policy check and the access and the loading is super fast. So then it trains the model and eventually it outputs. So the model is not big, so it's just for demonstration purpose. So the model trains very fast, but it gives you an overall like concept of how things happens. In real world, of course, when the model is larger, so this green bar will go just longer. So the overhead will be even smaller in terms of portion, how long it takes, the portion it takes. So because we have a runtime, so there must be a discussion about like how, like for example, a machine learning library like the LibONNX, which is an engine to interpret the ONNX when doing inferencing. So we run that benchmark with our system to see how the runtime and like library porting can affect the system performance. So what we do is that we put the LibONNX as a native. Generally, what you want to do when you're porting a library into a system like this. So you can see that this is the blue bar is like the vanilla one with no runtime or like our framework. And the green bar is ours. So it's like ours is how many times slower than a regular one. So if you look at the total part, which is about the entire, after running the entire benchmark, you can see that the slowdown is generally about 20%, which is similar to what you would expect when you have a runtime. For certain of these benchmarks that we have like 5 times or 6 times slower, that is because this particular procedure is just so fast that our overhead can take a little bit larger in the portion, but it's not like really taking so long. So the geomean is about 20%. So we showed about our design and architecture and also about evaluations, but like we only discussed the medical use case, but actually this, as you can see, this framework has many other use cases that can be used. So like for example, we can have a joint data analysis, like a bank, like multiple banks may want to do like fraud analysis. So they can see the traces from one bank to another to see like to see if certain account is involved in like money laundering. But that bank transaction is very like privacy related and confidential. So while they can be used for analysis, the bank to know about it. And we also want to output the output to be limited to the original bank where the fraud is found. So what's going to happen is that you can see these, so we can have policies on it. You can limit on the output, and you can also limit on input, like how the input cannot be leaked to a certain other party. So besides that, we can also have like we can also support. There are many cases like chemical compound development. A company may want to query another proprietary database. So currently, if you try to query that database owner will know like what you're querying, and they all know what you're trying to do. So this gave those companies an unfair advantage But now with our system, you can make sure the query is never leaked. But also the query result is also like strictly confined to be used for one company, not the other one. And also about smart home IoT, like this is also a very interesting story that we developed a more concrete use case on this for the CDCC. So for smart home, you have a lot of devices, but those devices generates data. The problem is you might also have a lot of like cloud service providers who's gonna want to access your data. Not only cloud service providers, but also like your contracted like home security company or home insurance company. They may want to access your data. But you can now have limitations on like what kind of specific type of data you can allow. For example, when your home has got a break-in, then they can access your video footage. But before that, they can't access. So you can have these kind of policies attached onto the data generated out of your home. So the project is not it's not perfect, and we have limitations, and we also have envisioned some future works for the project. So like one of the main part of this, how do we do this on hardware accelerators? Like we now have NVIDIA's like GPU TEs. Can we push our system to there? How do we apply the method to GPU, right? So there are new techniques called like the PCIe trusted IO. Like AMD has that, like Intel's proposing that. So how do we achieve that? So we can also have like formal verification on the middleware, because the middleware, as you can see, the middleware is where all the trust originates. So we have it to enforce all the sandboxing, all the IO control. So the full stack verification is required, but it's not entirely impossible because we already have a formally verified runtime, the MesaPi. So it's not entirely impossible. But on the limitation side, actually there's a trade-off when we talk about runtime sandboxing, is that the runtime sandboxing, so when you use a runtime, there's definitely a slowdown, but also there are many techniques to accelerate that, but those have like security like implications, for example, the AOT or JIT compilation. So there are methods to help mitigate those, like the SFI, the software fault isolation. We actually have a previous paper discussing about this technique called reusable enclaves. If you're interested, you can check those out. So these methods can be used to help, but they have a cost on the performance or the security. So this is a trade-off. So that basically concludes our talk, and we plan to open source this stuff. So the source code will be available after the whole thing get published. You can check. In the meantime, you can check our homepage. And thank you, and I'd like to take your questions.